Picture a blackboard in a hotel in the Pocono Mountains. It is springtime, 1948. My hands are covered in chalk dust. I am 30 years old. And sitting in front of me, watching me draw what looked like cartoon doodles on this blackboard, are some of the most fearsome minds in the history of physics. Niels Bohr is there. Robert Oppenheimer is there. Hans Bethe is there. Eugene Wigner. Edward Teller. Paul Dirac himself, sitting in the second row, completely silent. And I am drawing little wiggly lines, and little arrows and little dots, and saying these silly cartoons will solve a problem that has had every theoretical physicist on Earth tearing their hair out for 20 years. Bohr stands up. He marches to the blackboard. He looks like he is going to throttle me. It does not go well. I want to tell you that story. Not because the story is flattering to me, because it isn't. I made a fool of myself that day. But the cartoons survived. The cartoons spread. The cartoons got smuggled out of that conference by a young kid from England, and within a year every theoretical physicist who could draw a stick figure was using them. Within 15 years they had won the Nobel Prize. And today, every physics graduate student on Earth learns to draw them in their first year of school. They are called Feynman diagrams, and they are perhaps the strangest piece of mathematics ever invented, because they don't look like mathematics at all. They look like cartoons. So let me show you how a man got booed off a blackboard, and how the very thing he was booed for became the language of modern physics. To understand why these little drawings mattered, you have to understand what the world of physics felt like in 1947. 1947 was, in some ways, the worst year in the history of theoretical physics. Worse than 1900, when nobody knew what an atom was. Worse than 1925, before quantum mechanics was figured out. Because in 1947, we thought we understood the rules. We had Maxwell's electromagnetism. We had Einstein's relativity. We had quantum mechanics, all sewn up beautifully by Heisenberg and Schrödinger and Dirac in the 1920s. And we had stitched them together into a thing called quantum electrodynamics, which we shortened to KED, and it was supposed to describe how light and matter interact at the most fundamental level. Every chemical reaction, every flash of lightning, every photograph ever taken, every glance you have ever made at another person, photons bouncing off their face into your eye, that's KED. We had the theory. The equations were sitting on the page. Beautiful equations. Compact. Elegant. Gorgeous. And there was just one tiny problem. When you tried to actually calculate anything with them, you got infinity. Not large numbers. Infinity. The mass of the electron? Infinite. The charge of the electron? Infinite. The energy of an atom? Infinite. Try to compute how much an electron deflects when a photon hits it, and the formula gives you a number that grows without bound and never settles down. The theory was telling us, in the most precise mathematical language we have, that an electron weighs infinitely much. And of course an electron does not weigh infinitely much. An electron weighs about 9.1 times 10 to the minus 31 kilograms. We can measure it. We have measured it. The number is finite. Small, but finite. The theory was lying. This is what I mean when I say the field was tearing its hair out. Imagine you had spent 5 years building a stew. You went out and got the best cuts of meat, the freshest vegetables, the cleanest water. You followed the recipe perfectly, every step. And then you tasted the stew, and it tasted exactly like nothing. No flavor. No salt, no nothing, and you cannot find the mistake, because the recipe is correct, the ingredients are correct, the heat is correct. The stew should be delicious. The stew is bland. Some of the older men, the ones who had built the theory in the 1920s and 30s, started to despair. Wolfgang Pauli, who had a tongue like a razor blade, said that physics had reached an impasse and we needed entirely new ideas. Heisenberg suggested perhaps space and time themselves needed to be modified at very small distances. Dirac, who had given us the equation that started the whole mess, said openly that he believed the theory in its current form was wrong. Wrong. Not incomplete. Wrong. And remember, this is Dirac, the man who could derive antimatter from a piece of paper. If Dirac says the theory is wrong, the theory is in serious trouble. So that was the world I walked into. I had just come back from Los Alamos. I had spent the war doing calculations for the bomb. My first wife, Arline, had died of tuberculosis in 1945, 3 weeks before the test at Trinity. I was 27, exhausted, bereaved, and looking for something to do with my mind. A young assistant professorship had been waiting for me at Cornell, courtesy of Hans Bethe, who had been my boss at Los Alamos and who, incidentally, is one of the kindest human beings ever to have lived. I went up to Ithaca. Cold winters. Nice town. And I started to think about the infinity problem. Here I have to back up and tell you about my graduate school days, because the seeds of those Pocono cartoons were planted years before, when I was a kid at Princeton, working with John Wheeler. Wheeler was my thesis advisor. Wheeler was a marvelous man, the kind of man who took ideas seriously even when they sounded crazy, especially when they sounded crazy. And one day when I was 22 years old, I was sitting in his office and he said something that nobody had ever said to me before. He said, suppose the electron does not interact with itself. Suppose every electron only interacts with other electrons. Forget about the field for a moment. Just have particles, talking to particles, across space and time. This sounded ridiculous, because we knew electrons made fields, and the fields had energy, and the energy was real. You could measure it. You could feel the warmth of sunlight, and that warmth was electromagnetic field energy. But Wheeler had a point. The infinities in the theory came from electrons feeling their own fields. An electron sits there making a field around itself, and then it feels its own field, and the closer you let it get to itself, the bigger the field gets, and the bigger the energy, and bingo, infinity. So Wheeler said, what if we just don't let the electron feel itself? What if we say the electron only feels other electrons? And the field is just a kind of accountant, keeping track of who has paid whom. I worked on this idea with Wheeler for 2 years. We called it the absorber theory. It was bizarre. It involved time running both forward and backward. It involved the idea that a particle here, in this room, somehow knows about every other particle in the universe, all the way out to the most distant galaxies. And only when all of those distant particles agree to absorb its signal does the particle here even begin to emit. It is, on the face of it, completely nuts. Did it work? Sort of. It got rid of some infinities. It introduced new ones. But while I was working on it, I had to invent a new way of thinking about quantum mechanics, because the standard way, the way you learn in graduate school, did not handle this kind of theory at all. And what I came up with was something I call the sum over paths. Picture an electron. It sits at point A, and a moment later, you find it at point B. In classical physics, in Newton's physics, you ask, what path did it take? And there is one answer. It took whichever path solved the equations of motion. A straight line, a parabola, an orbit, whatever. One path. The path. Done. In quantum mechanics you ask the same question, and there is no good answer. People say, well, the electron is a wave, the wave spreads out, the wave does its thing, and then you measure and the electron is at point B. That's true, but it's not satisfying. It does not give you an intuitive picture of what is going on between the start and the end. So I said, what if we say something completely different? What if we say the electron takes every possible path from A to B at the same time? Every path. The straight one, the crooked one, the path that goes via the moon, the path that loops around backward in time. Every conceivable trajectory you could ever draw between those 2 points, the electron takes all of them. Each path gets a little number associated with it, a quantum amplitude, a kind of arrow pointing in some direction. You add up all the arrows from all the paths. The arrows mostly cancel each other out, because they point every which way. But some of them line up. The ones that line up are the ones near the classical path, the path you would have predicted from Newton or from the wave equation. Those reinforce each other. The crazy paths cancel, and what's left is the answer. This was a crazy idea. It was also, it turned out, completely equivalent to all the standard formulations of quantum mechanics. Schrödinger's equation, Heisenberg's matrices, my sum over paths, all the same physics, just dressed up differently. I included it in my doctoral thesis in 1942, and most of my professors thought it was a curiosity. Nobody really cared, but I cared. Because when I started thinking about the infinity problem at Cornell, in the cold winter of 1947, I had this picture in my head of every particle taking every path. And one night, working at my desk, I started to draw pictures of those paths. Lines crossing, lines splitting, lines going forward and backward in time. And the more I drew, the more I realized each one of these little drawings was actually a piece of the calculation. The drawing was the math. Let me tell you what was happening. When you try to calculate something in KED, what you really do is something called a perturbation series. The idea is you start with a simple, no-interaction picture of the world. Two electrons, sitting there, ignoring each other. That's easy to compute. Then you add a small correction, the simplest interaction, where one photon is exchanged between them. That's a little harder. Then you add another correction, with two photons exchanged. Harder still. Then 3, 4, 5. The series goes on forever, but each term is smaller than the last, because the strength of the electromagnetic interaction is small, about 1 over 137, a famous number called the fine structure constant. So if you compute the first few terms, you get an excellent approximation to the answer. That's the dream anyway. The nightmare is bookkeeping. Each term in the series, when you wrote it out in the standard way, took pages of mathematics. Pages and pages, full of integrals over four-dimensional space-time, full of products of matrices, full of subscripts and superscripts, and complex conjugates, and Lorentz indices. Just to write down the second-order term for two electrons exchanging two photons could take you a whole afternoon, and you would still have made arithmetic mistakes. People had tried to compute these things and gotten lost. Heisenberg had tried. Pauli had tried. They had all gotten tangled up in the algebra and given up. What I noticed sitting at my desk in Ithaca was that every term in the series corresponded to a particular kind of process. Two photons exchanged, that's a process. One electron emits a photon, the other absorbs it. Then a second photon goes the other way. You could draw a little picture of that. Two lines for the electrons, two wiggly lines for the photons, four little dots where the photons get emitted and absorbed. And every line, every wiggle, every dot in that picture corresponded to a specific piece of mathematics. The line was a thing called a propagator, which told you how the electron got from here to there. The wiggle was the photon's propagator. The dot was a vertex, where an electron and a photon meet, and that vertex carried a factor of the electron's charge. You multiply all these pieces together, integrate over the positions of the dots, and you have your term in the series. The picture and the math were the same thing. You could draw the picture and read off the math from the picture. Or you could write down the math and draw the picture from the math. Whichever direction you went, the bookkeeping became almost trivial. Anybody who could draw could compute. I cannot tell you how exciting this was. Calculations that had taken weeks now took an afternoon. I sat in my office with paper and pencil and computed the so-called anomalous magnetic moment of the electron, a number that experiment was just starting to be able to measure precisely, and I got an answer in agreement with experiment to better than 1 part in 1,000. I computed a thing called the Lamb shift, an energy difference in hydrogen atoms that Willis Lamb and Robert Rutherford had recently discovered at Columbia, and again the diagrams gave the right answer. I computed Compton's scattering, electron-positron annihilation, photon-photon interactions, and on every front the diagrams worked. But the diagrams had elements in them nobody could quite stomach. Things that made no physical sense. There were lines that went backward in time. Backward. A line representing an electron, traveling from later to earlier. What does that mean? An electron going backward through time? Of course, there is no such thing. But Dirac had shown, years before, that if you took the equation of the electron seriously, it predicted the existence of a particle with the opposite charge, the same mass, called the positron. The positron had been discovered in 1932 by Carl Anderson in cosmic ray experiments. And what I noticed was that a positron going forward in time and an electron going backward in time gave you exactly the same mathematics. Same propagator. Same vertex. Same answer. So in my diagrams, I just allowed time to run both directions and called the backward running electrons positrons. The cartoons happily contained both matter and antimatter, mingling with no extra rules. There were other oddities. Lines that started from nothing and ended at nothing. Closed loops, where a photon would briefly turn into an electron-positron pair, which would then annihilate back into a photon. These were called virtual particles, because they did not appear as actual measurable entities, only as transient blips in the middle of a calculation. And they were everywhere in the diagrams. Every diagram had little loops. The vacuum, in this picture, was not empty. The vacuum was a roiling soup of virtual particles popping in and out of existence. I should have been writing all this up. I should have been publishing papers. Instead, I was frankly drawing pictures and not telling anybody. I was talking with Hans Bethe in his office, scribbling on his blackboard, and Bethe was nodding and saying, "Yes, yes, this is good." But I was not writing down the rules. I had never been a writer. I liked to compute. I liked to play with the symbols. The idea of sitting down and writing a paper that explained the rules to other people, this struck me as boring. In the spring of 1948, Robert Oppenheimer organized a conference at Pocono Manor, a hotel in the mountains of Pennsylvania. This was a sequel to a smaller conference the year before, on Shelter Island, where the LAM shift had first been announced, and where the field had collectively decided that KED needed a complete reworking. Pocono was supposed to be where the new ideas got presented. About 28 people were invited, the titans of the field, and 2 young men were the main attractions. A fellow my age from Harvard named Julian Schwinger, who had been working out the same kind of corrections in his own way, and me. Schwinger went first. He spoke for almost an entire day. 5 hours, 6 hours, with a single break for lunch. Schwinger had developed a beautiful, mathematically watertight, exquisitely formal version of the corrected theory. He used a technique called canonical quantization. He made everything manifestly relativistic. He computed the anomalous moment of the electron, the LAM shift, all of it, and the answers agreed with experiment. And his presentation was a tour de force, a literal tour de force. He spoke without notes. He filled the blackboard with mathematics. The audience mostly sat there reverent. When he finished, Pauli stood up and called it the most beautiful thing he had ever seen. Then it was my turn. I got up. I walked to the blackboard. I started to draw cartoons, lines and wiggles and dots. I tried to explain what they meant. I tried to explain that this little squiggle here was a photon. This straight line here was an electron. This loop here was a virtual electron-positron pair. And the audience, who had just spent 6 hours absorbing Schwinger's high formalism, looked at me as if I had walked into the Vatican and started juggling. Bohr objected first. Bohr did not believe in trajectories for electrons. The whole revolution of quantum mechanics,